Good.
Alright. Hello everyone, my name is Cameron Hollenquist,
And I'm Ray Lunzer.
and we're going to do the calculus behind boats.
So why do we choose boats? Well, it's almost summertime, and we both love coming outside and stuff and doing boat activities. And also, we might want to make our own custom cargo boat for summer activities.
I personally love to canoe a lot, and I've always had those situations in the summer where I end up in the middle of the lake and I end up tipping my boat, or I end up bringing too much stuff and it ends up sinking. And so kind of learning how that actually works is fantastic for us. So one principle I want to explain to you guys is called Archimedes' principle. You guys probably learned about this in physics, but it was discovered by a Greek mathematician named Archimedes, and it states that it's a physical law that any particle that's completely submerged or partly submerged in water is acted upon by an upward force, or what people call the buoyant force, and that the buoyant force is equal to the weight of the displaced fluid. So this explains why sometimes a sponge would float, but a rock would sink, because in a rock the weight is more than the displaced fluid, but the sponge is less than the displaced fluid.
So then we have our problem. We wanted to figure out like what type or shape of the hull, just like the bottom of the boat, what would be able to carry more weight. And we picked between a flat bottom one, which is like it's like a deck boat. They use those normally in like Florida and stuff to go over like really shallow bodies of water. And or a round bottom hull, which is like canoes and like regular fishing boats that we have around here. And then we wanted to pick like standard dimensions, so like it would be somewhat similar. And 16 feet for the length, which is the classic fishing boat length. And then the height, which is actually like the depth of inside the boat, we just picked for 5 feet, just to have a standard depth. And then the width there, we actually got from the round bottom. We took the round bottom, we made it into a parabola, and we plugged the points into the distance formula, and got a width of 5.5902. Then we pick, so this number here we put into the formula for the parabola, just so it was an easy number. We wanted a standard number. It didn't really explain or like matter that much, because it ended up coming out as 5.59, which is about the average width of a boat, which is like 5 to 6 feet. So we just kind of got lucky with the guessing check there. Oh, and then the flat bottom hull. So here's like an example. We basically, this wasn't really our calculus part. We just wanted a part to compare it to. So the base times width times height, and we ended up getting cubic feet. And to get it into the buoyancy force, there's a lot of like conversions and stuff, because here you need acceleration, the volume of the fluid. We got the volume there, but like it was all in like meters and like kilograms. So we just put it into a buoyancy force calculator just to be more accurate. And we got that it could actually hold, or the force was 27,919 pounds. And then we took the gravity out of there just to find the weight that it could hold in here. And like with the cube, you like see this part, we just took that out because that's normally like above the water. And so then we got 2,848.878 pounds that you could fit in this boat before. That's the sinking point, like right as it's about to sink. You put any more weight in there, it's going to sink.
Okay. So I wanted to determine using the round bottom, and the calculus topic in this is using volume by cross sections, because we can't really find the volume of this because when we use Archimedes principle, we have to find the total displaced fluid. So there is a top function which is the horizontal line of the point where the boat goes above the water line, and also the parabola which is below the water line. So I wanted to use volume by cross sections because I wanted to cut out each individual piece into its own little parabola, find the volume of that, and multiply it by the length. So I just wanted to show you just how I got to that, where I wanted to take the height, which is the top function, by the parabola, which is ax squared, and I just use volume by cross sections to integrate and come up with a more general formula. So I didn't plug any numbers on this for right now, I just wanted to come up with like a general formula for this particular type of situation. And also, and just again to explain the distance formula, how we use the distance formula to find the width, where we take the same points where the square root of h over a, because if you do h is equal to ax squared, you would get the square root of h over a plus or minus. So use the distance formula, plug in the numbers that we've given you, and we'll find the distance between those 2 points. So this is just an example of just round bottom hull. As you see, it's very parabolic shape where it'll have a vertex at the lowest points. And what I came up with when I plugged in the general equation is 4 over 3 to the quantity of the cube root, the square root of h cubed over the square root of a times the length. So as we determined that the length is 16, the height is 5, and then the stretch of the hull of the parabola is 0.64. Plug that in, and we get 298.414 feet. So we wanted to compare that to weight. We converted that to weight. We took out gravity. Because we wanted to find the mass of the maximum possible mass instead of the weight, because we don't need to, because we want to consider just how much you can actually put on it without having gravity constantly pulling it down. So we took out gravity, and we came up with 1,895.33, or about 9 people.
So then it made sense actually, because if you think about it, the flat bottom it's more like a rectangle, and the parabola, the round bottom is like a parabola. So it made sense that the flat bottom would have more volume, which would make it able to hold more because it can displace more water. So then, so we wanted to figure out what could we all put into a boat that can hold that much weight, I guess.
So we did 4 little comparisons just to show you guys what we came up with and how much this boat could actually hold. So some might be serious, and some might be funny. So the average weight of a man is about 200 pounds, probably between middle age to older age. So we took our maximum possible weight for our boats divided by 200, and we get about 14.2.
Go to the next one.
Yep.
Oh, fidget spinners. We Googled online to figure out how many grams it was, and then we converted that into pounds, and we could hold 18,727, about that, 0.95 spinners.
Hold that much before the boat starts.
Put one more in there, it would sink.
Yes. We also want to just do some wheels. You can stick an average weight of a 2020 Polaris Indy 600, weighs about 473 pounds. If dry, without snow or any kind of liquid being affected by it or driving. So we took the maximum possible weights and we divided by the weight of each Polaris Indy 600, and we got about 6. We can hold about 6 before the boat starts to sink.
And then AirPods, they're 1.34 ounces, and 16 ounces are in a pound, so we divided that, and you could put 34,016 and a half AirPods into that boat before it sinks.
just a